Merci, Vytaute, et désolé pour les problèmes techniques. So let's go on and we do it online.
Okay. So thank you very much for the invitation. My name is Vytaute Pilipauskaite. I come from Aalborg University in Denmark, and today I will present parameter information of discretely observed interacting particle systems. It's a joint work with Chiara Amorino, Akram Heidari, and Mark Podolsky from University of Luxembourg. So for the plan of this talk. So we consider interacting particle systems, and first I will introduce a parametric model for it. I will then state the parameter estimation problem. I'll give the assumptions. I'll make the assumptions on the model under which we work. Some examples which satisfy our assumptions, and under these assumptions we have shown our main results, and I'll show you just the main ideas of the proofs. At the end, I'll present some open problems. Now, the model. So interacting particle systems have many applications. Here, just to name a few. In mathematical biology, one can think about large societies of animals that have some self-organization property. I mean, flocks of birds, herd of mammals, or colony of ants. So these are large systems of interacting particles that can also be a network, fully connected network of neurons that spike. Another application that is in social sciences, one can think about the particles as agents or human beings with that have their own opinion, dynamics, and seek for consensus. Another application in finance, it can be the risk in the system of banks, banks that borrow or to each other and lend money from each other, and in such a way interact. Also mean field games, so game theory, when we have a large number of players, that's another popular applications. And I hope that also in the future one will see applications in ecology. So now the interacting particle system. So we have a large number, capital N, of stochastic processes. Each particle process it evolves in R over a time interval 0 capital T, where T capital T is fixed. Okay, fixed time horizon, and the system satisfies the given stochastic differential equation for some parameter θ1 and parameter θ2, which will be the parameters of interest lying in some in the interior of some compact convex subset of RP1 and RP2 respectively. So this stochastic differential equation here, so one can see that for each particle, each process I, is driven by its own standard Brownian motion, and Wi, and these Wi's are all independent. The particle processes, so they have initial condition, so independent of the Brownian motions, Wi's, and these particle processes all start independently with a common given distribution mu0. So they are all ID initially. Now the processes evolve, and so we have the dynamics and we have the interaction with these coefficients B and A. Those are functions on the product space, from the product spaces to real numbers, and in the so one has a variable for the state of the particle, so in R, the value in R, and the value of measure, so in the space of P2, and this is a space of all probability measures on R with finite second moments, and one can have a distance, a metric there, take a Wasserstein 2 metric, with a reminder of a definition in the footnote. So the interaction is through this mu and t. This is the empirical measure of the system. Okay. So associated to this interacting particle system, it is this Makin-Vlasov stochastic differential equation. So when it arises when the number of particles ends and goes to infinity, this equation for one particle, it arises. So it's also driven by standard Brownian motions, where the process starts independently of this Brownian motion. And the interesting thing here that the same drift coefficient B and diffusion coefficient A here, they depend not only on the state of the process, current state of the process and the solution X bar, but also on its law distribution, mu bar T, current distribution. So, and the initial condition is the same here. So these equations, Makin-Vlasov, introduced by Makin in 1966, are also interesting from the analytical approach, because this law mu bar T admits a density under some nice assumptions, admits a density which satisfies a certain nonlinear partial differential equation. And one may be interested in properties of it. For us, what matters, that is the probabilistic property, that is the propagation of Kauer's property, the link between the interacting particle systems and this Makin-Vlasov SDEs. So if we have two collections, so we have interacting particle system and we have independent copies of these Makin-Vlasov SDE, where these independent copies are driven by the same Brownian motions as the corresponding particles, interacting particles, and start at the same initial, so the initial condition coincides. So then one has this this approximation, and there's some assumptions, nice assumptions to be stated later. So one has approximation that if I take a finite number k of in the system, so interacting particles fixed number k and independent Makin-Vlasov processes k, So as the number of particles in the system grows to infinity, one has this nice approximation. And these and other probabilistic properties have been studied by many people, and by Snitman, Méliard, Tanaka, Malurieux, Bolle, Guyan, Villani, Catio, and many others. So, however, statistical inference well is not so well studied and well developed, and that's what we are talking today. So one of the reasons is that that these collective dynamics, these interacting particle systems, are not directly observable, but now with the increase of data sets and data around one can also expect the statistical inference and the need to be one may need it. So these are the works in statistical inference for interacting particle systems or Makin-Vlasov processes that I know about. Parametric approach, non-parametric approach, and the very first name to mention here is Kasonga, 1990, who considered the estimation for interacting particle system, but observed continuously over a fixed time interval, where the diffusion coefficient A is just a constant, but B, the drift coefficient, depends linearly on the parameter, and linearly on the measure variable. So okay, so continuous observations, that was. Problem of this talk, it is so estimation of the parameter, however, from discrete observations of interacting particle systems. So we have n processes and discretely observed where the discretization step delta n, which is t over n, and t is fixed, and small n, it is the number of observations per particle, and both the number of observations per particle and number of particles, capital N, both tend to infinity. That's our setting. So high frequency. And this is a joint estimation, so for both parameters in the drift and in the diffusion coefficient. The estimator we define it as so of the true value of the parameter theta 0. So we define it as a minimum contrast estimator. We have a contrast function S given, and how do we come up with such a contrast function? So the thing is that we don't know exact likelihood of these discrete observations. So the solution is to approximate, and we use the Euler scheme. So if one takes the particle I, one just uses, so we are on a fixed time interval 0 capital T, and one just uses the Euler scheme to approximate the dynamics of the particle, and well, of course, the increment of Brownian motion which enters here, it is a normal 0 mean with the variance delta. So With this in mind, and recall that all the Brownian motions are independent, of course, with independent increments, one has one constructs such a contrast function, so it has the Gaussian structure, and that is the approach we take. We borrow this approach from the works. Florence, Zmiro, Yoshida, Kessler. So they use this Euler scheme contrast in case of the classical SDE. So if we want just have one process, one SDE equation, and the time horizon, then of course, if we observe discretely, but time horizon goes to infinity. So this is the estimator. Now the assumptions. So we work on the following assumptions. The very first two are standard assumptions. So that the initial conditions, so that the distribution mu0, where we start, has all moments finite, and that the drift coefficient, the function b, and the diffusion coefficient a, that those are global Lipschitz for any parameter value. So these assumptions give us existence, uniqueness of our particle system, also the propagation of chaos property. Okay, now the following assumptions. So the third, which says that the diffusion coefficient A is uniformly in X and mu and parameter theta2 uniformly bounded away from zero. And the second, so the fourth assumption, its first part, that the B and A as functions of the parameters, they are in C3, and all their partial derivatives up to order 3 have polynomial growth in X and mu uniformly in theta. So these two assumptions we use for in the proof of consistency of the proposed estimator. The second part, it's so here now the polynomial growth of these drift and diffusion coefficients is not enough. We also ask for their partial derivatives with respect to the theta parameters, partial derivatives of order 1 or 2. To be now also locally, so this is the first factor on the right, and the inequality locally Lipschitz, and then again polynomial weights, so polynomially growing. Okay, so the second part will come in the asymptotic normality. The fifth assumption, it concerns identifiability of in the proof of consistency. So identifiability, so we have two functions, I and j, introduced asymptotic contrast criterion functions, and that only the values so if we are away from the true parameter value, so either theta 01 or theta 02, that the functions I and j take larger values, much larger values. Okay. So the final assumptions again. So we're back to asymptotic normality. The first one concerns the asymptotic variance. We introduce the matrix sigma as a block diagonal matrix, where the block diagonal, on the main diagonal, we have the blocks that are square matrices of size P1, P2, and with explicitly given elements, entries, and the block diagonal matrix needs to be invertible. The final assumption, A7, concerns the diffusion coefficient A. Its specific form, however, still very general, and this one is also needed in asymptotic normality. So to really specify how this interaction in the diffusion coefficient, how it looks like. So we have the A tilde function, the dependence on mu then is of kind of a convolution type, and there is also given a function k, kernel function, and we ask these A tilde and k to be in C2 with partial derivatives of order 1, 2 of polynomial growth. So this is our list of all the assumptions. And we have examples that satisfy all of them. So the very first example, it is the Kuramoto model. So it's for the synchronization phenomenon. For example, in the clapping crowd, or so one thinks about n oscillators, and we define them by their angles. So each particle process stands for dynamics of an angle, and to be precise, we define the values modulo 2 pi. To be an angle, and we have evolution over fixed time interval 0 capital T. Now, the diffusion coefficient here is just a constant, theta2, the parameter, but the drift coefficient here, so it is a linear in the parameter, so theta1 is in front, and we have a convolution with a mu, so and sinus function. So this is a version of a well-known Kuramoto model. Another model, so this one is can be used for opinion dynamics. Again, the diffusion coefficient is A is just the parameter theta2 constant, but now the interactions, so that are in the drift, so how they appear. We have the differences in the opinion, so xi, xj particle, but also the influence function psi, phi with the parameter theta1. This influence function which acts also so on the differences of the opinions between agents. And we usually one could take a scaled indicator function, so that if that we have an amplitude and some range in which we are sensitive to the other opinion or not. So But to make things smooth, we take an infinitely differentiable approximation of this scaled indicator function. So that's a proxy. So that's our influence function phi. So that's a second example. So here we had the interactions, yeah, in the drift. But one can also extend to have the dependence on the particle, so on the particle process values, so to have this dependence in the diffusion coefficient. That's what is the third example about for. So the diffusion coefficient also depends on the value of xi. And in case there is one can take one of the parameters of this model, so theta 1 2, one can take it to be 0, so we don't have any interactions. Our theory will go through. So in case where all the particles are independent, and that would be a special case of the Pearson diffusion. And it also has applications in finance. The last example is the following. So we have interactions not only in the drift through this empirical mean, but also in the diffusion coefficient, and the mean field limit of this of the system. So one can refer to it as a time inhomogeneous Ornstein-Uhlenbeck process. So in case there are no interactions in the diffusion coefficient, this it's 0, and theta 1 1 is 0, that we come back to the model considered by Kassonga in 1990s. Now, okay, so our main results, so as I already announced, that's consistency and asymptotic normality of the estimator. And what matters here, that is that the convergence rate, so asymptotic normality, we can see that the convergence rate for the parameter in the drift and the parameter in the diffusion, it's not the same. We have two regimes, and that makes the proof, the analysis, a bit more complicated. Another important thing is here that one needs, for asymptotic normality, one needs to additional assumptions, so on the number of particles, capital N, and the discretization step. So for this to go to 0, and yeah, it's that, but that's only for asymptotic normality. Now to show these two results, we need some technical lemmas, and the very first two are classical assumptions. One has that uniformly in I, so for all particles, and uniformly in time, so all the moments are finite. Okay. And we also have a moment inequality for the increments of which also serves in the proofs, and is shown using Gronwell's lemma. It's classical. However, the following one, so this is the technical result, is not maybe not so yeah, it's not classical, but one takes a function on the product space again, so for the value and the measure, and if one has a Lipschitz continuity locally and polynomial growth, one can show this convergence in probability, which in principle combines Riemann approximation, so of the Riemann integral, and law of large numbers. Okay, for these interacting dependent particles. So this one, the second part is the second technical result is useful to study also the contrast function. So that's what we do. So in the proof of consistency for the estimator, the standard thing we need, so it is the uniform convergence of this normalized contrast function to these asymptotic functions j and I, uniform convergence in theta. And this one serves later for when we use the identifiability assumption, which gives that if we are far away for the estimator for the first parameter is far away from the true value, so then we know that there exists an eta such that eta I is also greater than 0 by it. And we just then what we do, we use the definition of estimator, so the fact that it minimizes the contrast function, and we use the second convergence, okay, this uniform convergence, to see that that this is vanishing in probability. And the proof is similar in the for the parameter in the diffusion coefficient. So it's the approach is classical. It's just that one needs to separate the two cases and find the right scaling of the contrast. The proof of asymptotic normality, this one follows also a classical route. So one uses the mean value theorem, and as a minimizer we have the gradient of the contrast that the value of the estimator is 0 vector, and that's the equation we are left with. So we need to introduce the normalization. So this is the matrix M on the, so for the first P1 diagonal elements, we have one scaling, the remaining P2 elements on the diagonal have the other scaling. And with this scaling, with this normalization, we isolate on the right hand side. We isolate the theta, okay, this factor. So we want that sigma. So this is the Hessian scale from the left and right. It converges to some constant. And we want the left hand side, the normalized to be asymptotically normal. That's what we need to show. So to show asymptotic normality, so gradient here we take it as a row vector. That's why we normalize from the right. So to show the asymptotic normality, we use we use so approximations to what we by a martingale array. So we need to show this very first convergence to zero. These are the conditional expectations up to moment g minus 1 delta. So this is for approximation by a martingale array of this. And then to verify the conditions for the central limit theorem, the central limit theorem, martingale central limit theorem. So for martingale difference triangular arrays, the two conditions for the asymptotic variance, and the second condition we take the fourth moments that one has the convergence to zero. So yeah, that is the approach we take. And the final, as I mentioned, so the scaled Hessian converges to the log diagonal matrix that is invertible, and the assumptions, our assumptions, and it converges uniformly. So for in S, so for the perturbations, it's fine. That gives the end asymptotic normality. So now the open problems, these there are quite some. So first thing to ask is efficiency, and we know from the works by Mark Hoffman and Letizia Della Maestra that, for example, they also take the fixed time interval, but continuous time observations, and the parameter is only in the drift, and the Fisher information matrix they get when they study local asymptotic normality, this is the one we also have, but only for the parameter in the drift. So we don't know about the diffusion. Another question you may raise also, this condition on the number of particles and discretization step, can one improve it? And we don't know for sure, but one may take a higher order approximation. So in the Euler scheme, one may take higher order approximations, and may in such a way one needs to correct to modify also the contrast function, but one may take this road to check if one can improve it, this condition. Also, what is interesting, the case where particles take values evolve not in R but in RD, and one can also take other assumptions, so different assumptions, not global Lipschitzianity for drift and diffusion coefficients, but other cases. And the case of jumps, so presence of jumps, it's also an interesting question. And in case of the classical stochastic differential equations, the same approach, this Euler scheme contrast was used in this case. So one may also try to see if something is possible to obtain. And of course, non or semi-parametric estimation of functions A and B. It's also, there are many questions, for example, if one has discrete observations. In continuous, it's known it's done by Mark Hoffman, but what if we have discrete observations? Well, what can be said? That's also open problem. So these are the references. So the talk is based on a preprint, and the two main works for this Euler scheme contrast. The idea for it comes from the works of by Florence and Miro and Kessler. So merci beaucoup pour votre attention.
Can I have a question?
Do you have questions? Any questions?
Okay. Paul? No? Okay. Can I have a question for you?
What?
Why do you need all those moments?
Can you hear me?
The moments?
Okay.
That's a good question. And one, in principle, does not need to have them all. But having A and B and their derivatives, partial derivatives, growing polynomially. So if one specifies clearly the order, one can, of course, restrict to lower moments this condition. And so the thing when one has this empirical measure which enters these A and B with a one can bound the things using the moments. So again, some finite moment, specific finite moment, if done properly, it's that would be enough. It's not necessarily true, not necessarily to have them all finite.
And the C inequalities are, for each case, there is a constancy.
Yeah, for each moment, one has a constant, and this constant is
uniform. Like exponential inequalities.
No. Just the constant is uniform in time and over the particles, and with the polynomial growth, when one just needs to bound the things, it's to show some term is fine, negligible. Yeah, it's enough.
You said about application. Did you work out applications?
Not yet, but I would be interested actually. I think yeah, even I think there are many people that work on the numerical schemes, and they use the interacting particles for the simulation of the Mike and Blasov SDE, and so the things are also doable in the computer. So I would also be interested to do statistics also, yeah, and on real data.
Sorry, there is one question from T online.
I will. I just yeah. Discuter. Okay, I I don't see where.
So maybe.
Maybe.
I don't hear. No, I asked her to put the display sound.
And
I cannot hear.
Or maybe I can.
Maybe you can write it. Or even if you want, make it as I don't write. I'm sorry, but maybe we first stop the video and then go on discussing.
Yes, I have another question. But simulate the process, you use the either approximation or you can there is other way.
Here it should work Euler.
Euler
Mm.
At the end you have a discrete process. No?
Yeah. So one should also be able to do it in practice and application on the simulated or real data. That would be interesting. Yeah.
I don't see. Maybe first we will stop the video.
Mm-hmm.